So finally, Einstein got rid of all this and just use these two uh, postulate, Jackson Hole postulate of relativity. So basically, it's just the saying that there are two principles. The first is the so-called principle of relativity, uh, or the postulate of relativity. This means that the physical law should be the same whenever you observe it in different reference frame. But for special relativity, the reference frame are restricted to what so-called inertial frame. The inertial frame is just wherever you have this Newton's first law satisfied. So basically an object without any forces just stay there or constant velocity. And any frame that moving using a constant velocity relative to this, the original inertial frame is still an inertial frame. Okay, that okay. Obviously, I mean, the people should ask the question whether we are living in an inertial frame because all our common experiment is based on the Earth. We live on the Earth. Is the Earth an inertial frame? Is it? well, the Earth is not a good inertial frame because there's the Earth. Obviously, there are different motion. You have the spin, right? Although it's not spinning too fast, and it's have this orbit around the sun. The sun is also moving relative to somewhere. So all that make it not inertial. And one thing, or another thing that make it not inertial thing is that the gravity. We're living under the gravity of the Earth itself, and the gravity actually make it a non-inertial thing. That in order to treat that, we need general relativity. So Einstein's idea of general relativity at first is try to build a theory of special relativity based on inertial frame, but then it generalized to non-inertial frame also. That's how that general relativity, the name implied. But the end of it becomes a theory of gravity because the two things are equivalent. Non-inertial frame, you have a whatever the inertial force, and you can treat it like gravity. And likewise, the gravity, you can treat it like in a non-inertial thing. So you can put it in the same language, but so but we actually all our experience based on non-inertial thing. So it's a little bit conceptually abstract for us to even think about inertial thing, but that's the starting point of theory based on inertial thing. Anyway, we'll hopefully, I don't know whether time to derive that, but just talk about this. We'll actually go to skip a lot of history and all that little things and go to the derivation of the Lorentz transformation. We probably don't have time to finish that, but just set up the problem. So basically, it's you assuming you have two frames, usually call it K frame, and then a K prime frame. I'm drawing a XYZ or whatever. I mean, Jackson like to use the Z along, and it doesn't matter. Just whatever it says. Prime Y prime Z. And now you have this constant velocity, relative velocity, like V is the velocity of the K prime frame moving relative to the K frame. So that's the velocity of the frame K prime. And then obviously the reverse is that the K will move in minus V relative to K prime. That is still true in special relativity. Okay. And now the second postulate is that the speed of light is the same as the in both frame, in all reference, all inertial frame. The speed of light, that is not obvious, but more generally, it's just assume that all physical laws are the same in all this reference frame, and all physical include the Maxwell equation as we written down the four Maxwell equation. In the four Maxwell equation for vacuum, the microscopic Maxwell equation predict the same C. For us, the C is whatever the coefficient in SI, C is 1 over square root of epsilon 0 times mu 0. And those are assumed to be constant. So if Maxwell equations are the same in all reference frame, it means the speed of light must be the same. Otherwise, you need to change the Maxwell equation according to whatever frame you have. But that is not the case. So we'll start with this to divide the Lorentz equation, but we don't have time. But have you learned this in other class? Do you take mechanics? Mechanics divide the Lorentz?
I learned it in
which modern field? I mean, not here. I mean, not here. So you're not taking classical. Classical is at the next year. Anyway, we'll divide that. It's very simple. I mean, it needs some thinking, but it's not difficult. And another special limit is the time. So you have the time coordinate t here, t prime here. And well, we usually will define t prime the starting point or the origin of the t prime such that at t equals 0, x the x prime equals 0, the origin of the k prime frame is the same in prime x also equals 0. It means that the origin of the k prime frame is at the origin of the k frame at t equals 0. Okay, so that's additional assumption. I mean, it just makes things easier. The transformation becomes linear rather than you need to always subtract by whatever the original time. So you just choose the reference point of the time so that the transformation becomes totally linear.